All right, we have a very important last topic here to add, which is what we've been assuming has been the case so far for everything was either the things bounce completely off of each other and 100% of the momentum goes from object A and B and back into objects A and B in some fashion, right? So it was either total bounce or it has been total stick together, right? The boy lands on the cart and they move together, or the train carts interlock and they move together, which works great for those situations and it makes sense. But there's a lot of other situations where it's not a totally 0% or 100% bounce or stick together, right? Something like the ball with the bat, right? We might be able to, put those two objects together and say, yeah, it's a pretty clean ding, right? Or maybe two balls that hit each other in pool, right? In a game of pool. Those clink pretty cleanly. There's not a lot of stick going on there, right? But what if it's something like a ball of mud, right? Or something like a vehicle impact, right? Where two cars collide. There's definitely some amount of sticking together, but also some amount of bouncing off, and it's not 0 or 100% one way or the other. So with those, we need to consider the impact, and the line of impact is going to be important, but especially the amount of what we call restitution, how much of the momentum is lost in the colliding of the particles and the squishing of them, right? That burns up some of that momentum. Some of that energy is lost just in deforming the materials. And so we need to consider what is that coefficient of restitution? How much of that is sucked up in the squish that happens? And so when we talk about impact, that's what we're talking about is the two objects come together and there is some deformation that happens. And, and so we're kind of breaking our rigid body rules here, but it's an important part of this conversation when we talk about momentum and transfer of momentum and conservation of momentum. So if we have two particles coming together, if they squish a little bit, they deform, they're non-rigid, then there's going to be some amount of that momentum that isn't accounted for if we just say conservation of momentum equation. And that amount of restitution we can quantify with this ratio of the change in uh, in velocities. We've got state two, so velocity B here, its exit velocity minus the exit velocity of A, and then the initial velocity difference. That's going to give us a coefficient of restitution, which will be unitless. It'll be a value between 0 and 1. And here's what we want to think about it as. If it's an elastic impact, a perfectly elastic where E equals 1, that means it's the total bounce, like we were talking about with the trains at the beginning, right? Bing, they just totally clink off of each other. Zero momentum is lost, and 100% of it is given back into both objects. So in a practical situation, that's really not possible, right? That would be like 100% efficient, which we know is not the case, right? There's always going to be some imperfections that make even the most perfect, right? Steel ball hitting another steel ball and they bounce off of each other. There's still going to be the slightest amount of squish that happens between those where some of that's going to get lost, right? But that is the ideal condition where E equals 1 is 100% of momentum goes back into both particles. And we can approximate that and we can use that assumption to do a pretty close estimation for a lot of situations, right? E equals 0, that would be the total plastic impact, right? Which is the opposite of elastic, where there's no separation, right? There's no bouncing back. They totally collide and the objects are together, right? This is the interlocking mechanism, or this is the boy landing on the train cart and they slide together, right? They're totally stuck together after the impact and they move with a common velocity. So it's kind of interesting. If we've got steel on steel, that sounds like it's a pretty non-squishy deal, but there's actually somewhere between zero point 0.5 and zero point 0.8, right? And these are tested values. So you get lead on lead is a lot squishier. Wood on wood, fairly squishy. Glass on glass, very not squishy, right? If you if you get much more than that, it'll just break. So glass on glass, like something like a ceramic ball that you play pool with, that makes sense. It's somewhere in that zone. So with that, we can now start playing with ideas where we even change the angle, not just a straight on impact, but if we have some angle that it comes in with, right, this theta 1, then object A could leave with theta 2, and we could have an incoming phi 1 and an outgoing phi 2 angle for object B here. But what we really care about is what is this plane of contact, right? What's the line at which those two objects meet? And so that is going to be really important. And we're going to be able to break this down into our two equations now to solve with. We've got our conservation of momentum equation just like before, but our second equation that'll make this possible to solve will be that E, coefficient of restitution equation, which is going to be, the relationship between the incoming and outgoing velocities, depending on how much that object squishes. All right, so the momentum is conserved only perpendicular to that line of impact. That's why that's so important to define what is that plane at which the particles are colliding. Because if you think about it this way, right, regardless of what directions they're incoming at, that line of the impact is the only line that they can give each other energy, right? If it's coming in at some angle, unless there's like some way that they're frictioning on each other, which usually we don't consider that during an impact, right? That the only impact that can happen is in the direction, where they're hitting each other. So that is the situation here, right? We've got particle A coming in with an x and a y velocity, right? It's coming up and to the right. And particle B coming up and to the left, but the impact only happens in the x direction in that case. So with that in mind, we'll do a couple of examples here with a impact and in particular with some angles that'll throw an extra bit of complexity in here, which makes it fun.